The two tests of time dilation. I'll do one story on the left and one story on the right. The story on the left will be microscopic in its nature. Is that the story on the left? I mean, story on the right is going to be macroscopic in its nature, so it's very small and large. We live in a macroscopic world. Electrons on the right, that would be microscopic. So first, the microscopic story. I have to introduce you to a particle called a muon, which is a fundamental particle of a charge of -1. I'll put it down here because I'm going to do a rudimentary decay equation. The mass I'm not going to be spelling out very well, but typically a muon is nice. It's nice to think of it as just a heavy version of an electron, and typically has a mass of around 200 times the mass of an electron. But once created, a muon doesn't stay in existence for very long, and it will quickly decay into a regular electron with a charge of -1, and an electron anti-electron neutrino, and a muon neutrino. All of these details are not really why we're introducing it as a character. What we're interested in is that the time it takes for it between it being produced and it decaying is something that we're interested in. And typically in the laboratory, it's measured to be around about 2.200 microseconds. Now, because in a lab, when the muon is not moving, its production and its decay happen in the same place, the same spatial place, so therefore we would put a subscript 0 on this and reference this as being that of proper time. So if we make now a comparison to experiments that they have done with muons that have been accelerated to a velocity of 0.9994 times the speed of light, c, we should be able to appreciate time dilation effects, because the average lifespan of a muon would be adjusted because of this motion. So if I get my calculator ready, we can do the calculation and find out exactly what's what. I don't know if you can see it on the camera, but I'm going to type out on the calculator anyway. So let's first by having a look at the speed parameter in this case, which would just be this number divided by the speed of light, which would just leave behind that number, 0.994. Let's have a work out what our Lorentz factor is going to be under these circumstances. That would be 1 over the square root of 1 minus 0.9994 squared. So on my calculator, 0.9994 squared equals 1 subtract that answer equals square root that answer equals 1 divided by that answer equals. So we would have a Lorentz factor of around 28.872, in which case our time dilation effects, our new time period between the generation and decay of a muon particle, should be equal to 28.872 times by 2.200 microseconds to give us, let's say 2.2 equals 63.5 and some change microseconds. And lo and behold, when they reproduced this in the lab, they found that they achieved a similar time for the duration of a muon when it's fast moving that matched Einstein's predictions within the experimental error. So there's one experiment there. The second experiment is a slightly larger story, and it was performed in 1977 by two scientists. One was called Richard Keating and the other one Joseph Haffel, and it's known as the Haffley-Keating experiment. And in this experiment they had a series of atomic clocks which are super accurate, and they kept one of the clocks on the Earth, and then they mounted some other clocks on some aeroplanes, and one of them flew around the world in this direction, and then they flew another airplane in this direction. Round and round the world they went. And when they got back, they compared these clocks that were on the plains to the clocks that were supposedly at rest on the Earth. And they found that the time dilation between the clocks was within about 10% of the values that were predicted by Albert Einstein's theory. Later on, in the University of Maryland, they repeated a similar experiment, flying aeroplanes around and round Chesapeake, and they found that they could reproduce the same results, but now within a 1% error of those predicted by Albert Einstein's theory. Today, if you were to transport, so if you were to say FedEx an atomic clock from one place to another, you would have to take into account the dilation caused by their motions when transporting an atomic clock. So today, when atomic clocks are transported from one place to another, for calibration and other purposes, the time dilation caused by that FedEx movement has to be taken into account. So let's have a look at a checkpoint question, if you like. So let's start with some plain paper. And let's set up a story, and the story will involve some train tracks. Let's draw those here. And the story can involve you standing by the train tracks there. And as you're standing by the train tracks, a train carriage travels past you at relativistic speeds. Whoosh. Okay. So whatever this velocity is of this train carriage, it is relativistic, such that it is a significant fraction of the speed of light, such that we can observe some relativistic effects here. Okay, inside the carriage, with his back to the front side of the carriage, is a really short, indoors world's tallest shaved Ewok, also known as Mr. Watling. So over here is you, over here is indoors tallest shaved Ewok. And Mr. Watling has a laser pen, and he shoots the laser pen with a pulse of laser light, so I'll put laser pulse, from the front of the carriage to the back of the carriage. So this is the story. You're on the train tracks. A relativistic train carriage passes by at a significant velocity, such that it's a reasonable fraction of the speed of light. Inside the carriage is Endor's tallest shaved Ewok, Mr. Watling, and he fires a pulse of laser from the front of the carriage to the back of the carriage. So, checkpoint question. Part A: is your measurement of the speed of the pulse greater than, less than, or the same as that measured by Endor's tallest Ewok? Question part B is Mr. Watling's measurement, or is Endor's tallest Ewok measurement of the flight time of the laser pulse a proper time? Is the time it takes for the laser pulse from the front of the carriage to the back of the carriage, whatever time Mr. Watling records there, is that proper time? And part C. Part C. Are Mr. Watling's measurement and your measurement of the flight time of the laser pulse related by the equation delta t equals the Lorentz factor times delta t0? So you would be delta t, Mr. Watling would be delta t0. Would this equation link Mr. Watling's observations about time relating to the laser starting from the front of the carriage to the back of the carriage to your observations of the laser pulse front of the carriage to the back of the carriage? Okay, in the next lesson we're going to have a look, this is next week's lesson, we're going to have a look at the relativity of length.